All right, guys, I'm going to pick up right where I left off on this problem, example 3. If you don't know what I'm talking about, then you didn't watch the full first video, so make sure you've done that before starting here. But if you're ready, we'll go ahead and get started. I have to answer this question. Is the sum of two rational numbers always a rational number? Something I want to talk about real quick before we get into this, I want to take a little bit of side notes, right? So remember, hopefully you're doing all this at home. You're writing these problems at home. You're writing these notes at home. Or obviously, if you're in class, make sure you've done this in class, right? So we talked about sets last time at the very beginning of topic 1.1. Now, the main reason for that is because we classify numbers in sets. So, for example, I want to first start off with real numbers. So real numbers is literally like every number that you can possibly think of, okay? It goes like 1 to 27 to 1/3 to -28, 0, pi, 3.1415, whatever, right? All those numbers are real numbers. And you're probably like, well, why is that even a classification? Well, there is something called imaginary numbers, but we're not going to get into that. That's not until algebra 2, so don't worry about that. But real numbers is basically every number you can even imagine, any numbers that shows up on your calculator. Those are all real numbers. Okay, so that's a set. You have a set of real numbers. Like I said, that's everything under the sun. But in that set, there are subsets. So subset, for one example, we have a subset called rational numbers. So I'm going to make it kind of like a tree here, right? Rational numbers. You also have a different subset called irrational numbers. I guess I'll just leave this red for now. So you have two groups, rational and irrational. Now, rational is most of the numbers that you would typically think of. So the difference between these two sets, now remember, both of these sets are considered real numbers. They both come from that set, but this is a smaller section of it. Rational numbers focuses on a particular group of numbers, and irrational focuses on a different group of numbers. So a rational number is basically anything that doesn't have a repeating random decimal. An irrational number always has a repeating random decimal. So let's say repeating, and again, write this stuff down. Make sure you're taking your notes as well. Repeating random decimal. So that's really all irrational numbers are. They're the very, very strange numbers. So for example, pi is an irrational number. Let me pull out my calculator and let me type in pi real quick just so you can see the actual number. So if I hit pi, hit enter, right, you get 3.141592654, and then it just stops there for now, but it does continue going, right? You know that pi never ends. The numbers after the decimal go on forever. This is just where the calculator decided to stop it, right? Pi is an irrational number, and this is all it takes to be irrational. It just means that your decimal goes on forever with no pattern, okay? So decimal goes on forever with no pattern. So decimal goes on forever with no pattern. Now, a lot of the times, though, we see these numbers come from square roots. So this is the thing you really want to look for when you see square roots. You want to think it's probably irrational. So let me take the square root of any kind of random number. Like let's say the square root of 5, right? Square root of 5 gives me a repeating decimal that has no pattern, and it will go on forever. So square root of 5 is an irrational number, right? So if I do it again, let's do square root of 12. Right? Again, I'm going to get a decimal that goes on forever with no pattern, right? So a lot of times these are all irrational numbers. The square root of 5 is irrational because its decimal will go forever. Square root of 12, irrational. Square root of 33, right? all of these are irrational. So a lot of times, you're going to see irrational numbers. You're going to see them really look like the square root of something. Square root of 5, square root of 12. I'm just going to list some examples out, right? Square root of 12, square root of 33. When you see that square root sign, you really kind of want to think irrational. However, there is there's a couple exceptions to this, and that's it. That's something called perfect squares. So if you see, for example, let's take the square root of 4. It's got the square root, right? So you think, oh, it's a square root number, so it might be irrational. But actually, square root of 4 is not irrational, right? It doesn't have a decimal that goes on forever. It's just the number 2. So that's actually not irrational. This one, the square root of 4, would actually be rational. Other ones, like the square root of 9, that's also rational because, again, you see it doesn't give you a decimal that repeats. You do square root of 16. That also doesn't give you a square root that repeats, right? Or a decimal that repeats. It's just a number 4, right? These three, the square root of 4, the square root of 9, the square root of 16, are going to be rational. So what I really want to say is irrational is really going to be these square root numbers, but with the exception, and you should make a note of this, exception of perfect squares. So that, I'll just give you the list, right? The exception of the square root of 1, 4, 9, 16, 25, 36, 49, 64, 81, and we'll just stop at 100. There are more numbers than this, but these are all perfect squares. So that means if you take the square root of any of these numbers, you're actually not going to be irrational. But if you take square root of like any other number, like for example, the square root of 5, you see the 5's not on this list, right? Square root of 5 is going to be irrational. Square root of 12. Again, 12 is not on this list, right? Square root of 12 is not on that list, so it's going to be irrational. 33, it's not on this list, so it's going to be irrational. So if I try to say the square root of 50, again, it's not on this list, so that's going to be irrational. If I say the square root of 85, again, 85 is not on this list, so that number is irrational. But if I say the square root of 64, 64 is on that list, so it's not irrational, okay? So just make a note of this list, because if you see square roots of any of those numbers, those are the only ones that won't be irrational. But a square root of anything else will be irrational. Now, if you're wondering where these numbers come from, some of you might already know, some of you might not. These numbers are perfect squares, meaning that they come from a number multiplied by itself. So 4 is 2 times 2, 9 is 3 times 3, 16 is 4 times 4, 25 is 5 times 5, 36 is 6 times 6, right? And that's the same here, 7 times 7, 8 times 8, 9 times 9, 10 times 10, right? So that's what makes those numbers the exception. So obviously you can keep going, right? 11 times 11 would be 121, so that would count. That'd be a part of this list. 12 times 12 would be 144, so that would count. It'd be a part of that list. So you can add them if you want to. Typically, we don't see numbers bigger than that, so I kind of just stop it there. But yes, there are more exceptions than what I wrote here. I just only went up to a certain limit. Okay, but the general rule of thumb is if you see a square root and it's on this list, then it's not irrational. But if you see a square root of a number and it's a number that's not on that list, then that number is going to be irrational. Okay, so let me say that one more time for it to sink in. If you see the square root of a number that is not on this list, so like the square root of 90, see, notice how 90 is not on my list here, then that means that that number is irrational. If you want to take a calculator and check, you can. See, if you type in the square root of 90, square root of 90, you'll notice, right, it's going to have that long decimal. So that's why, again, it's irrational. So just, if you want to use a calculator to check, by all means, you're free to do that. All right, but that's what irrational is. Rational is every other number, okay? Now, rational is actually going to be broken into even more groups. So rational can also be broken into a subset. Remember, rational and irrational are just a subset of real numbers. So another subset of rational is something called integers. All right, and a subset of integers is going to be whole numbers, and I'll explain what these sets really mean, what numbers are in these sets. And then a subset of whole numbers is natural numbers. Okay, so irrational is just irrational, right? It's going to be those weird square roots. But rational numbers can be broken into even more different categories. So rational numbers include basically, rational, let's do some examples over here. Rational fractions are rational. So 1/2 is rational. Decimals that go on forever but have a pattern. So for example, 0.333 repeating. It goes on forever, but it has a pattern, right? It's not random numbers like all of these, right? The 4, 8, 6, 8, 3, 2, 9, 8, 1, right? That's all random, right? These decimals here, there's no pattern to them. That's why they're irrational. But if you have one with a pattern like 0.333 repeating, that's rational, okay? Regular numbers like 12, right? Or 0. Numbers that you're typically used to seeing, right? Those are all rational numbers. It can be a fraction. It can be a decimal. For example, 0.5, that still works, right? It can be a decimal like that, or it can be a decimal that goes on with a pattern. It can be regular numbers like 12. It can be negative numbers. It can be negative 13, right? All of those are rational, okay? Now, integers are going to be basically whole numbers and negative whole numbers, okay? So you guys know what I mean by whole numbers, right? Like 7, 8, 9, 10, right? Not 10.5, right? No decimals, no fractions, just whole numbers and negative whole numbers. So let's write that up. Whole numbers and negative whole numbers. So this would be like the numbers you write on the number line, okay? So think integers, think the number line, typically. So when you draw a number line out, you put 0 in the middle, you put 1, 2, 3, 4, right? -1, -2, -3, right? These are all integers, okay? That kind of pattern, right? No decimals, no fractions, okay? Decimals and fractions are still rational, but they're not considered integers. Just a heads up with that. Now, whole numbers are going to be not negative. So, whole numbers again. You know that it's 1, 2, 3, 4, 5, right? Those are whole numbers. So basically, no negative numbers. Not negative, but keep in mind it does count 0. It counts 0. So basically, whole numbers would be 0, 1, 2, 3, 4, 5, right? Whole numbers, you know what those are, but not negatives. But it does count 0. Natural numbers is the exact same thing as whole numbers, except the only difference is natural numbers don't count 0. So whole numbers, but not 0. And this is, again, no negatives as well. No negatives here. No negatives. So natural numbers are just numbers you count with. So 1, 2, 3, 4, 5, right? If you're going to count how many kids are in class today, you use natural numbers because you start with 1 and then you go 1, 2, 3, 4, 5, right? So natural numbers are just those. So that's how all of those things, all the things I mentioned here, are rational because they're all part of that rational group. Okay? Irrational, like I said, was its own little ballpark, its own little stuff. All right. So I really wanted to make sure that we were clear on those two. So now let's get into answering the question. Sum of two rational numbers always a rational number. Is this true? Now remember, a rational number can be, anything that doesn't have a decimal that goes on forever without a pattern. So rational numbers we talked about, it can be 0.5. It can be regular numbers like 12. It can be fractions like 1/2. It can even be decimals that go forever, but with a pattern, as opposed to ones without a pattern, right? It can even be negative numbers. Okay, these are all rational numbers. So the question is, if I sum means add, if I add two rational numbers, am I always going to have a rational number out? So for example, let's take 0.5 and 12, right? If I add those two numbers, right, that's a rational number, that's a rational number, what do I get out? I get, in this case, 12.5, right? That's a rational number. This is rational because it doesn't have that decimal that goes on forever, right? If it's is it ever going to somehow turn out to be 5, 3, 9, 1, 6, 8, right? Repeating, is that ever going to happen when I add these two numbers together? No. So this answer here is still a rational number. And that works with other decimals as well, like and fractions, anything that's rational. So like, for example, if I did 0.33 repeating and I added it to 12, then I would have 12.33 repeating. But again, this is rational, and this is still rational. It does have a decimal that goes forever, but it still has that pattern, right? It's going to be 3s that go on forever. So it's still a rational number. So there is, in this case, when you add rational numbers together, yes, you're always going to get a rational number out. So the answer is, yes. Is the sum of two rational numbers always a rational number? Yes. Now, let me explain the solution that they spit out to you here, because it's probably going to confuse you. Well, they have some examples like I did, right? But let me go to some of this. Okay. Let me try to explain what they're writing here so it makes a little sense to you. So in math, we consider irrational numbers like fractions, as in a over b. Now, what this means, when you see these numbers, when you see this a over b, a just means any number. So like 1, 8, negative 10, right? It doesn't matter. Just think of a whole number. Think of it, or an integer, right? Integers, remember, are like whole numbers and negative whole numbers. So a, b, c, and d, they just represent a number, right? Like these, for example, like these numbers, right? But a just means it can be any number. It doesn't have to be 7, right? A, it's just going to be any. It could be any number once, right? B can be any number once. C and D can be any number once. So this is saying if I had a fraction and I added another fraction, basically a rational number, and I add another rational number, what am I going to get? Well, when I do my whole like denominator thing, common denominators, and I add things together, this is still a fraction. It still has two numbers on top, these on the bottom. It's still going to be a fraction. So, for example, 11 over 5 plus 1 over 6, right? It ends up equaling another fraction, 71 over 30. So this is just what we call a proof. If you want to take time to screenshot this or write this down, it's helpful. But this is something that you want to get, this would be known as a proof. Oops. As a way of saying any generic number plus any generic rational number, right, is always going to equal some generic rational number. So just kind of a quick way of using letters. We use letters just to represent numbers of all sorts, right? To represent all the numbers rather than having specific examples like these. These just represent any possible number you want. So it's just there to be a generic or general statement. But yeah, somewhere in your notes, let's write this stuff down. I want you to write down somewhere on the side, okay? Here, let me go back to this. Somewhere on the side of your notes, let's start writing some of these down. So a rational plus a rational equals rational. Write that down somewhere. Keep a little box chart thing because we're going to need it, okay? For like a little shortcut. So rational plus irrational is equal to rational, and this is always. All right. So let's move on to the next one. Is the product of two rational numbers always rational? So what that means is if you multiply them together. So let's see, can I open another one? Can I do another one of these? I think I can. Yeah, it does. Okay, cool. So product means multiplying. So again, rational numbers are going to be 12, it can be 0.5, it can be 0.33 repeating, it can be negative 13, it can be 1/2, whatever. If you multiply these numbers together, are you still going to get a rational number? Well, let's think about an example, like 12 times 0.5. Well, 12 times 0.5 is 6. So this is a rational number. 0.5 is a rational number, and it comes out to 6, which is also a rational number. So it works there. What about some other cases? What about, negative 13 times 1/2? Well, this ends up being negative 6.5, which again, this is a rational number. 1/2 is a rational number, and negative 6.5 is a rational number. So it's true here. We have a rational times a rational, and it equals a rational. So in this case, it's also going to be true. So what I want us to do is add that to our list. So rational times a rational equals a rational. And this is always true. So whether you add them or multiply them, rationals together equal more rationals, okay? Again, they show the generic one where you have A over B just being any number, right? A being any number, B being any number. Same thing with C and D. When you multiply them together, you get these two fractions, so you just make another fraction. So a fraction, a rational number times a rational number just makes another rational number. That's all it's trying to say there. So again, keep that in mind. So is the quotient of two rational numbers always a rational number? And the answer quickly here is yes. I'm just gonna, yes. Quotient means dividing, so a fraction divided by a fraction, which seems weird, but it's essentially the same thing as multiplying. So I guess we can add that there. Rational divided by a rational is going to equal a rational. Again, this is always. So again, this is going to be a cheat sheet for us in the end. So if you're keeping up with this, this is going to be our cheat sheet. Something to keep kind of everything all together concise. All right, so we've covered that. Let's go on to example 4. Which is this one. I want to do this one. All right, now this one has a little video. You're welcome to watch it. It sort of explains a little bit better than I was explaining the whole rational, irrational thing. So I'm going to let it play real quick. Let me see. I don't know how you guys are going to hear it, but you might be able to hear it. I'm going to let it play and let you watch it, and then we'll move on, okay?
Is the sum of a rational number and an irrational number a rational or irrational number?
Oh, I gotta play.
Write the sum of an irrational number and a rational number as a rational number. Every rational number can be written as an integer divided by a non-zero integer. So for a divided by b and p divided by q to be rational, a, b, p, and q are integers with b and q not equal to 0. Solve the equation.
So quickly, what that was just saying is A, B, P, and Q are just any random numbers. But they, to make a fraction, it's a rational number. A rational number is just, it can be any fraction with any integer number. So A, B, P, and Q, just any random numbers, right? The important thing here is C is an irrational number. So think like the square root of 5 or the square root of 12, those other ones that we saw earlier. Think of C like one of those numbers.
For C, first, subtract a divided by b from both sides of the equation. The equation becomes C equals p divided by q minus a divided by b. Write the right side of the equation with a common denominator. The equation becomes C equals p times b minus a times q divided by b times q. In the equation, the numerator is an integer because it is a combination of integers by multiplication and subtraction. So p times b minus a times q is an integer, and b times q is an integer not equal to 0.
So basically what that's saying is if you have an integer on top of another integer, then you have a rational number. What's going to happen here? Well, if this is a rational number, then C can't be irrational because we said C was irrational, and it can't be both. That's what they're going to say here.
Therefore, P times B minus A times Q divided by B times Q is a rational number. This is equal to C. But from the given statement, C is an irrational number. But this is a false statement. A number cannot be both rational and irrational. So what went wrong? The mistake was to assume that you could write the sum A divided by B plus C in the form P divided by Q in the first place. Therefore, the other choice, the sum must be irrational, had to be.
So basically it's saying by writing the statement and assuming that the answer was going to be rational, came to this contradiction. This is what we call proof by contradiction. We assumed that it would be a rational number, right? A rational plus an irrational, we assumed to be irrational. And it turns out it can't be, right? Because of the contradiction. You're saying C is rational at the end, but at the beginning you're saying it was irrational. So because of that contradiction, this hypothesis that they would both, a rational plus an irrational would equal a rational number, that hypothesis was wrong. So what this ultimately means is that, let's add to our cheat sheet, a rational number plus an irrational number equals an irrational number, and this is always. So a rational plus an irrational is equal to an irrational number. And you want to think about it in, let's look at a calculator. Let's take a rational number. So for example, let's just take, let's take 25. 25 is a rational number, right? Oh, I gotta go back down. All right. So let's take 25. It's a rational number, right? Let me try to add it to an irrational number. So an irrational number, an easy one would be like the square root of 5. Okay, if square root of 5 is irrational. So I have a rational number plus an irrational number. And what do I get when I hit enter? I get a decimal that's really long and doesn't repeat. Or, it goes on forever with no pattern, right? We have that irrational look to it again. So a rational number, 25, plus an irrational number, the square root of 5, ends up being this irrational number. So that's why we've set it on the list. The R rational plus irrational equals irrational. That's always true as well. Oh, I hit the wrong thing. It's all right. Close that. Close this. I didn't want to open that. All right. So let's move on to the next one. All right. Is the product of a rational number and an irrational number rational or irrational? So again, the question here is, for a cheat sheet, we're going to have a rational number times an irrational number. And the question is, what's it going to equal? Will it equal a rational number or will it equal an irrational number? Well, let's see what they say in the video.
Is the product of a rational number and an irrational number rational or irrational? Write the product of a rational number and an irrational number as a rational number. By definition of a rational number, A, B, P, and Q are integers, with B and Q not equal to 0. Solve the equation for C. Multiply both sides of the equation by the reciprocal of A divided by B.
Now, you guys follow along with this. You don't have to, you're not going to be asked to work this out. This isn't like an example you have to work out. This is just trying to prove how to get the answer. Okay, it's just going to answer the question, but it's showing you, it's explaining to you how it gets that answer. Okay, so you're not going to be required to do this. You're just going to have to be required to understand why the answer is what it is. So this is just trying to explain it to you.
Or B divided by A. Since A times B times B times A equals 1, the equation simplifies to C equals P divided by Q times B divided by A, or P times B divided by Q times A. P, B, Q, and A are integers. The product of two integers is an integer. So P times B is an integer and Q times A is an integer. Because P times B is an integer and Q times A is an integer, C is the ratio of two integers. So C is a rational number. Since we started with C as an irrational number, now C is both rational and irrational. So the assumption that you can write A divided by B times C as P divided by Q at all is wrong.
So what happened here is the exact same thing in the last example video that we did, right? We assumed the answer was going to be rational in this proof, and it turns out we assumed that it was going to be rational as the answer, but then we came up with a contradiction that C ended up being rational. However, we said in the beginning C was irrational, so again, it can't be both. So that must mean the assumption was wrong. So it can't be rational means that the answer here is that they would equal an irrational number.
Of the equation by the reciprocal of A divided by B, you were dividing both sides by A and 1 divided by B. Also notice that in order to divide by A when calculating C, you have to assume that A is not equal to 0. If A equals 0, then A divided by B equals 0, and A divided by B times C equals 0 for any number C. So the product of a rational number and an irrational number is always irrational, unless the rational number in the product is 0.
I really wish I could hide. I'm trying to get rid of this thing at the bar at the bottom so that we can read this. But that last statement right there that they just said is extremely important. Okay, so if we're adding this to our cheat sheet, rational times an irrational equals irrational, but not always. Okay, the exception is if rational is 0. So unless rational is 0. So it's not always going to be irrational. There's only one time where it wouldn't be irrational. So let me pull up my calculator to give you kind of a number example, right? So let's do the same numbers we just did. Let's do 25, a rational number, times, so we're getting multiplying in this one. Let's do an irrational number, square root of 5. So here I've got a rational number, 25, times an irrational number, square root of 5, right? So when I do that, I get another irrational number. I get 55.9016, right? A decimal that goes on forever, no pattern. So that would make me think it's irrational, right? But the one exception is if the rational number, instead of being 25, what if I use the 0? Because 0 is a rational number, right? So if I use 0 and I times it by any irrational number, so again, we can use the square root of 5, right? When I do this rational number, 0, times an irrational number, square root of 5, I get 0. Now, see, 0 is not irrational. 0 is a rational number. So this is the only time where you multiply those two together, rational and irrational, and you actually end up with a rational answer. So that's why I said here, rational times an irrational is irrational unless the rational was 0, unless the first number here was 0. Because if that number was 0, the answer is going to be 0, which means that the answer would then be rational. Okay? So something that kind of, a little weird one for you there. But again, that's why we have our cheat sheet. Okay? Let's look at the next one. All right, is the difference of a rational number and an irrational number always irrational? So difference. Difference means subtraction. Now, subtraction is really the same as addition. So if you're doing a rational plus an irrational, or if you're subtracting a rational minus an irrational, I'll put a minus sign here as well, just to indicate both, right? It's not really going to be different. You're still going to get an irrational number as the answer. So this one's asking if you subtracted a rational number and an irrational number, is the answer always irrational? And if you're subtracting, the answer is yes. Subtracting is going to be the same as addition. You're going to get the answer as yes. But obviously, remember, multiplication is going to be different. It's not always irrational. It's only unless the rational isn't 0. But that was, remember, that question was asking about adding or subtracting, not multiplying. All right, so we've done those problems. Let's try the next example. So we'll try one more example real quick. All right. Is the sum of a rational and an irrational number a rational or irrational? Well, we've already answered that. Did I click on the wrong thing again? I don't know. We didn't. I didn't click on the wrong thing. I think it was just showing the same video before a different example. Or maybe we did do it. I'm not sure. It's all right. I think we get the idea. I want to add to this list, I think, real quick. Let me think. Okay. What an irrational number times, let's actually do plus first, plus another irrational number. This one's going to be irrational again, always. The last one is irrational times another irrational. This is only, this could be both. It could be, this one could be either rational or irrational. So I'm going to say irrational, but there's an exception. Unless both numbers are the same. So let me talk about this last one real quick. An irrational times an irrational. Let me grab my calculator. So if I take an irrational number, like the square root of 5, and I try to multiply it to another irrational number, so let's say the square root of 12, right? I'm going to get an irrational number. Again, that decimal that repeats, or it doesn't repeat, but goes on forever, right? So an irrational times an irrational gets me this irrational answer. But there is an exception, because this isn't always going to be irrational. The exception is if both irrational numbers are the same. So for example, the square root of 5 times the same exact thing, the square root of 5. So both of these are irrational. Square root of 5 is irrational, and square root of 5 is irrational, right? So you have an irrational number times an irrational number. But the issue is on this one, I get the answer is 5, meaning the answer is actually rational. So the answer here, irrational times an irrational, most of the time is going to be irrational, but it will be rational if both numbers are the same. So unless both numbers are the same, then it would be irrational. Okay, but just keep that in mind. It is possible it won't always be irrational. It could be rational or irrational, just depends. All right, but there's your cheat sheet. This is the two main ones to point out really are these multiplication ones, the rational times irrational and irrational times irrational, because they have some exceptions, but everything else works all of the time. I'm going to close this cheat sheet out now. So if you need to write it down, just pause the video. I'm going to get rid of that. All right, that's going to answer it for those. There is one more thing actually I want to discuss with you guys. I'll just snip this screen so I can do it on this. And that's number classification. There's a couple of questions in the homework that ask this, so just real quick. So there's real. Let me put up the little cheat sheet. You got real numbers, and in that you separate them into rational and irrational. But rational also gets broken into integers on its next step. We've already made this. Hopefully you already have this in your notes, so you don't have to rewrite it again. Whole and then natural. So hopefully you already have this in your notes. So you're going to be given a number. Let's start with the number 5. And then you need to ask, which of these categories does it belong to? And 5 is, it's a natural number. We'll start from the bottom. It's natural because remember, natural numbers were all the numbers you'd count with. So 1, 2, 3, 4, 5, 6, 7, 8, right? Which means it's also a whole number because all natural numbers are part of the whole number group, right? Because whole numbers are 0, 1, 2, 3, 4, 5. So it's natural. It's also whole. Remember, all the whole numbers are integers, right? Integers are -1, -2, -3, but also the positives 1, 2, 3, and 0, right? This is also an integer because remember, all whole numbers are integers. And since all integers are rational, this is also rational. And of course, since all rational numbers are real numbers, that means it's real numbers as well. So number 5 would actually be all 5 of these categories. So you're going to have like select all problems, select all that apply, and you would select all of those. So let's try a different example. Let me give you a different number. Let me go with the number -5. Okay, slightly different. Now, -5 is not a natural number because natural is only positive. So it's not natural. It's not a whole number either because whole numbers are 0 and positive. Whole numbers do not include negatives, so it's not a whole number. But -5 is an integer. Integers are the negative numbers. This is where the negatives come in. Integers are -1, -2, -3, -4, -5. Also, they're also 0. They're also 1, 2, 3, 4, 5, all the positives as well. But -5 is an integer, right? It is negatives to be count as integers. And since integers are all also rational, this is also rational. And since rational is also real, this is also real. So you would have those 3 selections. So let's try another number. Just a couple more. If you already understand this, if you think you got this, then you can just skip. You're good for the rest of the video. But if you still want a few more practice, let me give you more practice. Let's do a fraction, like 1/4. Now, 1/4 is not a natural number because it's not, a positive, or it's not like a whole number. It's not a whole number either. Obviously, it's not whole. It's not an integer because integers are whole numbers, positive and negative whole numbers. But it is rational. This fraction will be rational. It's not natural, it's not whole, and it's not an integer, but it is rational. And since it's rational, that means it's also a real number. So notice everything's going to be a real number. There's no number that's not going to be real. So everything's going to be real. Keep that in mind. But the question is, what other categories does it fall under? Now let's do the square root of 18. Now, if you remember the list I gave you earlier, 1, 4, 9, 16, 25, 36. You remember these numbers you wrote down earlier, that list? These are the exceptions to the rule. Now, 18 is not on that list of numbers. So that means the square root of 18 is not going to be rational or any of the rational types. Square root of 18 is irrational. So just irrational. But of course, rational is real as well. So we'll say irrational and real. So the square root of 18. Now, if I do, for example, let's say the square root of 25. Remember, when you see square roots, you want to think irrational unless it's on this list. 25 is on that list. So 25 is not actually irrational. 25 is actually going to be rational. Now, there's actually more than this because square root of 25 is real. It's a different number than what we think it is. For example, type in the calculator. Square root of 25 is actually the number 5. And as we said earlier, the number 5, it's a natural number, it's a whole number, it's an integer, it's rational, and it's real. So this is really the number 5. So it's all those other things. It's an integer, it's a whole number, it's natural, and of course, the end all be all, it's real. So that one's a little tricky. When you think square root, your instinct is to think irrational. But if it's any of these numbers, if it's any of those exceptions, 1, 4, 9, 16, if it happens to be anything like that, like the 25, then it's actually going to be all of these other ones. It's actually going to be all the rational and everything from there on out. So the natural, the whole, the integer, all of that stuff. If it's one of those on the list, okay? But if it's not one of those on the list, like 28, if it's not on that list of numbers, and you take a calculator and you try to do it, for example, the square root of 28, that's just irrational. It can't be any of the other ones. It's just going to be irrational. Okay, so the square root of 28 would be irrational and real, obviously, because if it's irrational, it's real. Everything's going to be real. So the square root of 28 would be irrational and real. If you have other questions or you want to see me do more, just let me know. Send me a message. I'll get back to you. I know this video was kind of long, but that wraps things up. So, bye.